So we can.
Good afternoon, everyone. Welcome back after the lunch break. The first talk after the lunch break is going to be by Dr. Bipin Kumar, one of our co-organizers. Bipin is a senior scientist at High Performance Computing Systems, HPCS division of IITM Pune. Bipin's main focus is computational science. He has completed his undergraduate graduate studies with major in mathematics, followed by MSc from IIT Kanpur. He was Ratish sir's student, that is a previous speaker. He earned his PhD from NUS and
No.
sorry from this Dublin City University in Ireland, where he worked on high performance computing. After his PhD, he shifted his focus to atmospheric science and spent 5 years of postdoctoral research in Germany, including 1 year at Max Planck University Institute for Meteorology in Hamburg. So Bipin has wide experience in parallel numerical algorithms, high performance computing, this DNS for cloud microphysics, and also he's working in the AI and ML domain also. He has received various scholarships such as the DCU Teaching Award, the Microsoft Ireland Scholarship, and also the NUS Research Scholarship. So with
Okay,
that,
thank you, Adway.
I hand it over to Bipin.
So this is the post-lunch talk, and so I have the responsibility to make you keep you wake up, because after lunch people can sleep. And so what my talk is not a very like undigested food kind of thing. It is just like a dessert after the food. So it is very simple. I'm not going to talk about any much model or something. Something I will talk about as a case study for a model, but I'm going to talk about the how to do the data pre-processing. Everybody talk, we all talked here, all the speakers, all the, I mean, the AI models and all, but everything is data driven approach. So the main pillar is the data. So you have to first think about how to handle the data. That is what I am going to talk. So that's why I put the title, the role of the data pre-processing in the AI model, especially for the meteorological applications. So first thing is the why we have to do the data pre-processing, that you might be knowing already. So I will show you some examples of gridded data, radio sounded data, radar data, satellite data. Suppose you get the data, then what happens? So if you are working already in this field, you might be knowing, but still I will just give some example. Then I will take a case study of the PM 2.5 data, which we call it the we develop a model for the fire location forecasting, but it is basically the forecasting of the PM 2.5 at different area. The thing is here that we have the data from the same source. The data is coming from same source, but when we are developing a model at a different geographical location, we have to change the model. So that is what I am telling about the property of the data. So what we do in the data-driven approach, we just think about, okay, I am going to work with this particular problem. If it is a data-driven approach, first thing we have to worry about the data. From where we will get the data? Okay, data source. That is the biggest problem till now. If you want to work in some particular area, if data is not available, then you cannot. And so what are the data required? Then what are the data source? And then you get the data, whether you can get it or not. You know that data is available, whether you are, you are able to get it or not, that is also a question. Sometimes it is difficulty. We face the difficulty to get the data. Okay, once you get the data, then what is the next step? You have to understand the data. In particular, what is the time resolution? What is the spatial resolution? And what is the time period we got it? So suppose you want to do the nowcasting. What time resolution you want to, your input data should be what time resolution? Suppose if we get the 1 day data, 1 day average data, can you do the nowcasting for the few minutes, few hours? So if we are going to do the nowcasting for next 1 hour or 2 hours, what kind of data is required? Hourly or sub-hourly? Maybe half hourly or 15 minutes or something, no? So that is what you should understand, what is the time resolution. Now I am saying that suppose you want to do the nowcasting for a city. If the data is, the spatial resolution is 20 kilometer or 10 kilometer, is it enough to do the city level nowcasting? So now the question is, when you get the data, suppose you are getting data from unknown source, you download it, you know somebody gave you the link, you downloaded the data. First thing is, you have to see based on your problem whether the data is suitable or not. So then you have to see all these things. Also, for the nowcasting, if you have a data, suppose the half an hour resolution data, if you got for 2-3 years, 5 years enough. But if you want to go do the short range forecasting for next 4-5 days, then the 5-year data, daily data is not enough, no? So the time duration is also important. Everything based on your problem statement, what problem you are going to handle. Okay, so suppose everything is decided. You got the, suppose you are going to do the nowcasting, you got a very high resolution data, some instrument, maybe radar data, something, everything you know. But then you got suppose 5 years data, 15 minutes. And then what I have to do? How much gap is in the data? Many times it happens that instrument is not continuously working. Sometimes some maintenance is happening, no? So there will be some gap in the data. So what kind of gap it is? Whether it is gap in the time or whether it is a spatial also. So suppose there is a city and we have got a radar data and there are 2 radars. One thing is radar may not be working. Another thing is everything is not covered somewhere, some spatial gap will be there. So there can be a gap in the time, there can be a gap in the space also. The next thing is the data distribution, how it is distributed. How many people already thought about this when you work on the data? And if I see the distribution, what kind of distribution is good? I already wrote it, but have you think about that why we should have a Gaussian distribution? Or if it is a skewed data, is it okay? We don't have to bother about and just start developing our model because we know this is the model, these many layers we can do. We have downloaded the model from the GitHub. We can work on our data. So is this important to see the distribution? And if it is, then why? Yeah, so this is the problem. Model training will have the problem. Okay. So, okay, another thing I have to specify here. Suppose we are working some problem statement where the target variable is 1, but we have many input variables. I will come to when I go to the case study, I will tell this thing. So in that case, we have to have the same time and spatial resolution for all the input data. These are very basic things, but you have to always keep in the mind. So whenever you are going to start a problem, you have to note down in your notebook that what are the things before starting training. Okay. And if there is any gap in the data, what are the methods you are going to apply to fill that gap, to fill the data, imputation of the data? There are many techniques, mathematical techniques, I mean, you call it machine learning techniques, and there are some scientific way to do that. I mean, you have to think physically whether it is correct or not. So, data distribution, suppose this is the data. Can we use directly? It is skewed. What to do? We have to go up to this way. How to go up to this way? That you have to decide based on the data characteristic. Okay, so as I said, if the data is not properly distributed, what can happen? In the data distribution, even the previous talk, the whole detail mathematics was told by Professor Bipin Kumar. We are going to optimize the loss function. When we do the optimization, what we generally are going to do, gradient descent method. Gradient descent method, what it will do? It will take some approximate solution and start going to the solution space and finding the solution, and it will minimize the error. That is what the optimization thing. So the gradient, I should not go there. So gradient should find some minima. If the data is not properly distributed, Gaussian type or normal distribution, we will find this kind of problem. So we will have the many local minima, and then the solution will go, solution will oscillate in this way. Then you say, oh, your training loss is going come and down, come and down. It is not converging properly. So that's why we have to first make the data distribution in a proper form. Okay, this is something I just put it in the continuation, but you all know, you have seen the data, you have, you know now what are the data gap, you will do the data imputation, but then the thing is how much data we are going to put for the training and validation and testing. So this is a general rule, but is it strict? We can go in this way? Yes, so you see that you are saying that we can change here, we can inverse 20 or 30. So validation can be 20 and testing can be 30. 10. Yeah, I mean, there is no like very strict rule that you have to go 70 plus 10 plus 20. Sometimes we are putting this here also, we are putting 30 to 40%. It all depends what kind of data we are taking. But normal, we are going in this way, 70%, 10%. Okay. Another thing, this is just what is the overview of the data-driven approach. You have already seen this. I'm putting, I mean, just putting a revised version. And next step is, whatever the data, we have some data range A to B. It can be 0 to infinity. It can be some range. Okay. We are doing the normalization with using the standard method, max, min, or whatever the things. We are going to do all the training is happening in 0 to 1. That everybody know. But the reason behind it? No, nobody told before. I think there were some basic talks were there. Yes. Yes. This is one of the reason. If we have the multi-input and they have the different unit, okay, so the variation will be too much. So everything, all the data should be in the same range if they all are the input. Then we are going to train, then we are going to use that optimization function del or del L over del theta 1 or WI, the differentiation with respect to the weightage. Okay. Fine. So then finally what we do, once we have done this, then we will go through the model training and then model testing. Model training is, these are the main step which even Ratish sir also told. Hyperparameter tuning. Number of layers also, you can say this is the part of the tuning, model tuning, and the loss function definition. You have been listening to many talk, what is, how we can define the loss function. Even sir told in the previous talk that we can go MSE or MAE, but if it is like a differential equation kind of things and we are doing PINN, we have to define our own function. Or if you are going for gain methods and all, then there is a perceptual loss. So you have to define your own loss function. Or maybe you can develop, even in some of the this forecasting method, we have also developed our own loss function. We can define our own loss function. Generally, we are going for the MSE and MAE. Or then this is the steps. Fine. So they just brush up the things what we do in the data-driven approach. Now, I don't know how many people have seen this data, and my slides are not very new. Some old slides I am referring. So this is a IMD gridded data, precipitation data. Suppose I have got the data. My problem statement here is that I want to do the 3 days weather forecast, the precipitation forecast. This is a daily data, and it is the rain gauge ground observation data. And I want to do the weather forecast here in this area. And generally we take a either rectangular or the square area, because we work on the matrices when we do the convolution. And I'm going to apply some convolution method, convolution STM or something. Now the question is, if you see, we don't have the data here because say ground observation, we don't have data here. It's ocean, other country, we don't have. So if you get the data, I mean, many people must be working with the IMD gridded data. If you get the data directly, we will get the minus 9999 something, wherever data is not available. This is the standard way, I think, IMD put this way, no, Rajiv? So some, okay, whatever, we don't have the data here, and we want to do the training. Negative values, negative value we are not going to use for the training purpose. Then people will say, okay, we can put the nan, but nan is also not recommended to do the training, but not a number. So what it will train, what it will, put the weightage. Then happily we will say, okay, substitute 0. What is the problem by substituting 0 here? All the nan we can put the 0. This particular data, every data has its own characteristics. Yes, you got it the point. So if, see, this is almost 70%, I think. And in the model, if you are telling, okay, this is all 0, that means you are saying there was no rain. It is not correct. I don't have the data. I don't know, but there was a rain in this country. There was a rain in all these area in China and all, and the ocean. But I don't have the data because it was a ground-based observation. But if you tell to the model, then you are giving the wrong information. So the features will be captured by the CNN and all, it will be wrong. So putting the 0 is not a solution. What to do? The thing is, like, if we are in the real space, the value here in this case, what is the range? Is 0 to infinity, and infinity will be our like maybe 100 or 80 or something. That is the maximum rainfall in a day. So this 0 to infinity, and we cannot put the 0. 0 is the meaningful value here. What we have to do that we have to transfer some other vector space, some mathematical space, so that we can change the range. So what we have done, this is all the data pre-processing. Look at, I have not gone up to the training part. So first, we have tried many space and all. So you can go any exponential, logarithm, some other space. Then what we have done, we have found that if you go to the exponential space, we are good enough. Now substitute 0. What will happen? Our range has changed from 0 to infinity to 1 to infinity. Now what is happening? The meaningful data has gone from 1 to infinity. Now you substitute 0 and give this to the model for training purpose. What model will understand at every epoch? Oh, this 0, this is not meaningful. Our data is 1 to infinity. We have to work on the 1 to infinity. These are the practical approaches which we have done. It is not coming from the mathematical derivation or something, but this came with the experience, with the many students work, and we found, okay, this way is better, but there must be some mathematical way, like Professor Ratish was discussing. So now here 0 has a no meaningful value. So we have very nicely, we can put the 0 and then we can train the model. Okay, so this is the way how we are going to handle the data. See the another data. This is example 2, radio sonde data. This is the radio sonde data, and all the details are there. We have the humidity, relative humidity, different level. But 10 years of the data, all I have written. But what I want to say that this is the data distribution. When we got the data, this is the data distribution. So now what is the problem here? It's a simple time series data. It's a radio sonde. Negative value. Also, negative value we can discard. We can take it from 0. So we can take it from 0. But still, suppose I discard that much. Then range is small. No, this is humidity. I can take data from 0 to 100. Discard the minus and discard the greater than 100. Shall I go to my first slide? Yes, the distribution. The distribution is the problem. I told you, if we take this kind of data, we will have the convergence problem. The optimization function, when we are going to optimize it, the convergence problem will come in the gradient descent method. So Yeah, as I said that we can cap this from 0 to 100, and we can do all other kind of things. Then the thing is that what kind of transformation we should use for this particular data so that we can get a proper distribution. So previously I said we concluded that we can go e to the power ax. What is the value of a, which I have not discussed, it depends. But in this case you see that what kind of the transformation we have used, and we have different variable, we have to use the different transformation for this. So if you see that here this is box Cox we have used. So from this distribution we came to this distribution. So once we are coming from here to here, we are in the good shape. That's what initially I discussed. The data should be normalized, a normal distribution, Gaussian kind of distribution. Just, I mean, this is the final transformation I am saying. We have used many, but this is the transformation box was which gave me the proper distribution. So remember, this is from the raw data to the just distribution we are seeing. Initially, whenever we got the data, we have to see the distribution and then try to put into the Gaussian kind of distribution. Here also, this is 815 different, but this is all RH. This kind of distribution we converted into the Gaussian distribution. So there are 2-3 types of transformation we have used. This Yo-Johnson transformation successfully handled the zero. Box-Cox transformation we gave to the proper distribution. And this is all the work is just like a master student did. So the students, I mean, any new person, for me it is like any master or BTech student, they are coming, give the data, they will start working. Once the result doesn't come, then they will come to you, oh, I'm not getting the result. The correlation is 0 or correlation is 0.2, and what to do? So that's why I thought that I should tell this thing into the workshop before jumping directly to training a model. You have to work on the data. You have to analyze the data. You have to understand the data. Okay. This is the another data. This is a Doppler radar data for a particular city. What the radar will do? Radar antenna just gives this emits the waves, and we get the reflectivity. From the reflectivity, we get the data, and from if the voice is proper. So in the radar data, what kind of difficulties you can face if you want to work on the meteorological variable, suppose precipitation? No, I'm saying the first thing is the as it is data, you are suppose live data is coming. You have the access to the live data from IMD radar or some other radar. What are the difficulties? And this is a Doppler radar. It has a radius of the 200 or 300 kilometer, and you have the access to the data somehow. Data calibration is one thing. First thing I am saying that I have to work on the meteorological variable. I'm giving the hint in this way. What radar can do? Radar is just sending the waves coming as a reflectivity. It can be anything. It can be a bird, it can be an aeroplane, it can be a hail, it can be a cloud, and it can be the raindrop. But we are worried about only, we are interested only raindrop. So first thing is the filtering. And there are many, and it can be even flies, this small flies. They also get reflected and we get the data. They are not the droplet. Now the question is, I don't know if somebody is from radar meteorology, they must be knowing well. I'm not from that area, but I have to work in the data. That's why I have to be, think about it. So suppose you get that this is the size, maybe 100 mm or just a droplet, but a small droplet size. Droplet is 1 millimeter and half, less than that. And we got the data. Can you recognize that whether this is a fly or this is a rain? Okay, so I just told that the complexity of the data. There are way. We will just see the height, from which height we got the data. So there is a way that flies, they go a particular height, but droplet comes from different height. So there are many ways. So first thing is, if you really have the direct data access, you have to first filter out those reflectivity which is important for you. If you are going to work for the rainfall, you have to find the only rainfall reflectivity, filter it out other. If you are just want to know the population of the flies and all in particular location, then you have to just filter that much reflectivity, that okay, at different height and size. One thing is this: suppose we have got, in my case, I'm working with the radar scientist, IMD or IITM scientist. They are very good, good scientists. They are directly giving me precipitation. Okay, one thing, we get the reflectivity, not the direct variable. Even if we get meteorological, the rainfall things, it is not precipitation, it is the reflectivity. So then the people have the formula, this formula, which I am not going in detail. But what I am saying that, yeah, if you are directly working, you have to first convert from reflectivity to precipitation if you really want to give a forecast of the nowcast of the precipitation. Otherwise, you can go directly for the reflectivity as well. Okay. So in my case, I got suppose this data. This is the rainfall. But what is the coordinate of the radar? It's a polar coordinate. And how we are working in the computer vision? XY coordinate, Eulerian coordinate we are working, and then we do the convolution and all. So even if you get the data from a radar scientist and you got your choice of the variable, they are not going to convert. So you first have to see what is the coordinate. So from the, see, this is the reflectivity to rainfall. You can either you have to do or you will get it in this way. Then from polar coordinate to Cartesian coordinate you have to do. Okay. And then now you are in the Cartesian coordinate. And this is the distribution. Or if I say that even somebody help you, there is a group and somebody is doing the radar things and somebody is doing the converting from the reflectivity to the precipitation and polar to Cartesian, and at the end you get the data. In the Cartesian coordinate, you got the precipitation. Will you work on this data? And you know the source, you know the problem statement. We are going to work on the nowcasting of a particular city. Can you see this? Can you believe this data and work on this data? See the x-axis range. What is the problem on the? This is the frequency, this is the range. This is the precipitation in millimeter. Yes, if it is a nowcasting, 15-minute interval or half an hour interval data, can you think in half an hour we will get the 1000 millimeter? From where? It cannot happen. Even not in the cloudburst and anything. In any case, it will not be in 15 minutes that much. But the data is showing some values are there. So that means this data is, you have to filter it out based on your problem statement. Finally, we have we say, okay, the maximum data which we kept it, we are finding from a particular range, 0 to 8 millimeter is reasonable for 15 minutes. Okay. So first thing we have done the data capping here. Then again, actually this is not always required to convert into the, in this particular case it is not required, but somehow the students who are working, they went directly jumping to this function and they got the good convergence and they got the good result. But in this case, actually it is not necessary because we are already on the land. So there is not a much problem. But anyway, this was done and then we have converted again into the exponential space. So till now, there is no model training. I did not talk about any model, which model. I'm not even talking which model I have used here. In the next slide, I will tell. So now you think you are going to develop a small model, nowcasting model. And even I'm telling you take the vision transformer or you take GNN or you take convolution, something, whatever the model even I'm telling. And writing a code, how much code is 100 lines, no? That also you are picking something from the TensorFlow library or the PyTorch library, you will pick up and this. How much time it will take? Maybe half day or even less. Think about the whole project if you are going to do, how much time is required for the data pre-processing and then the result analysis compared to the coding for this Python. Any just guess? Writing the code and submitting the job in the GPU and get the result. That much time writing the code and the whole project starting with the problem statement, get the result. So how much percentage you are spending on the data analysis or data pre-processing or handling the data, I will say, overall. 50 to 70%. Any other guess? Speak. If I am either teaching or I am giving a lecture, I am very interactive. I will, and already I said it's a post lunch. I don't want to let you sleep at all. 50 to 70% is reasonable, but some people believe it can go up to the 90% also. It all depends. See, if I say apply the convalescentium method, you know what is the convalescentium, immediately you will go and download from the GitHub or somebody has, it will take 5-10 minutes, half an hour, and you will code it and you will just start running it. It will take 1 hour. But understanding the whole data and doing all those process, and if you don't know how, I mean, what kind of data you have to plot it, this and that, it will take long time. I mean, I'm also saying that 50 to 60% time you have to spend. But recently some professors, IT professor told, no, I'm telling you it can go up to the 90% also. It all depends, problem statement, data source, okay, and the type of the data. Okay, so now I think, still example 3. So this is here I have used the convalescentium method. One more thing which is now it is not much important. Generally people go for the iterative method. But sometimes what you do that you want to do the forecast for the next 5 lead time step. So you will develop a model. Okay, I'm giving the past 10 time step. I want the 5 next time step. I will generate a model giving 10, give the get the 5 directly, which we call it the direct. No, this is what splitting. This splitting will also depend what kind of model we want to develop. Whether you want all the 5 time step in one shot, or you go, what is the other way? We want the 5 time step. So we have the data t minus, I will say that tn minus 10. Okay, last, and we want the tn plus 5. The model will give this data, we will give directly, we will get the 5 time step whole data. Is that the correct way? This I call it direct step. And already I said now there is a fixed standard. Now people know that what to do. Okay, anytime have you studied the linear system of equation in mathematics? Solving the matrix equation Ax is equal to B. If it is a sparse matrix, we have different method. If it is a dense matrix, we have the different method. What are the two methods? Huh? Elimination. Elimination is the direct method. Gaussian elimination, this and that, and then reducing. And there are iterative methods. So what I said here, this is basically direct approach. You are giving the 10 time step previous and getting the next future 5 time step. This is the direct approach. But if you see the theory, mostly people will say, no, we will not go, because if you do directly, it will not give the performance because all the numerical error will propagate at the same way. Instead of that, you get the one time step, giving the 10, get the first one, then this first one put back into the input, so that previous 9 and this 10, they get the 11th one. So then it comes in the corrected way, and in the forecast is, and then the forecast is better. Okay. So here what I am saying, that this is the input sequence. I am giving the 5. I want, in this case, I took the 5 previous and giving the 5 next. But it is not like I am giving directly 5 now. This is the final output. So this is 1 by 1. I think, do I have? Okay. I don't have all the things in detail because I'm not discussing the model here, but I'm telling how we are doing. So this is the 5 time step I took. 5 I got it outside, but in the terms of iterative approach. So my idea here is to tell about the data pre-processing. So I'm not going in detail. So I'm just putting this flow chart. It's already in a paper here. It's already published paper. So we have the data, and we did all the data pre-processing, exponential, this and that, and then supervised splitting. The splitting, how we will do based on our approach, how we are going to develop the model. And then this is the overall thing. So from pre-processing part, post-processing part, I put 50 to 60%. It is very optimized way I put it, so that people don't think, oh, I am doing the coding, everything I do, and you are saying my part is only 20% or 30%. But it is like that. Coding is not too much. It is not like C coding or Java coding. Okay, it is just writing some routines you are taking. So most of the time you have to worry about the data. What the data you got it. That's in the pure data-driven approach. Once you have the solving the differential equation, PINN and all, then you have to worry about the initial and boundary condition and how you are going to develop the loss function. Okay. Now, one idea, example I gave, the now casting. Now I'm telling that what happens when you just take the data and just make the model without thinking about many other things which I discussed. So this is a case study. It's a published work. We want to do some kind of fire location data. It came from one particular source. It is a satellite-based data and converted by the in a gridded data by the NCAR people. And our target is to forecast the PM 2.5, which we decide, we indicate as a fire location. It is like either a stubble burning or some other way. So I will not go much, but I am saying that this is the total data, and the resolution of the data is 0.01, but not all the variables. These are the variables we are going to consider as a input, as a predictor. Okay. So first thing is, the data was satellite data. It is covering everything. If you take look at here, the data is covering everything. And the size of the data, this work we started 4 years before. That time we did not have the even much facility for the GPU, but we have now. And the data was 5 terabyte. So 5 terabyte, in which GPU you are going to train it? So what we have to do, the data when it is coming in the whole Indian it's the whole globe data. Then we got it in Indian subcontinent. Then finally we thought, okay, we will first go to the location wise. I will come back to discussion what is the problem when we go location wise and using the same model we cannot use. So first we got this one, this NCR area, Punjab, Delhi, Haryana area, and we develop a model. One student worked and we develop a model. Okay. Look at the data distribution. This is the max mean. We do not bother about. When any new student comes, now we are teaching them that they are telling through the workshop and all, but before people are not worrying about much, no. We developed a model, he developed the model, and we used the Cornwall STM, all kind of things. We have decided what this is the training, validation, this and that. Finally, this is the result. What is the result? And this was a 1-year master project from IISER Pune student. And it took him, because he's a mathematics student, It took him to understand the whole problem. It took 1 month or something to tell. I was telling that what is the problem. And then he was a data science student. He just started working as a data. Okay, and then once it is trained and all, it was very difficult running on the parallel GPU. That time also parallel writing a MPI code for the parallelization of GPU, it is all difficult. Even now also difficult. Parallel CPU we can do, parallel GPU is difficult. Maybe sir will tell more about it, he's from NVIDIA. Now everything available, but in 2021 and 22, it was not so easy. We did not have even facility. That time you did not give us to your parallel GPU facility. Now we have, okay. Fine. So this is the model. We develop 5 layers and correlation coefficient is this. After that, he came to me like even now students are doing. I said the previous student from this radio sound data. She's just currently working, just finishing the thesis. She's from Pune University, and she worked with his supervisor for maybe 5-6 months. Finally, when the result came, they both came, oh, I'm not getting the result. What is this? The correlation is only 0.5, not going more than that. And we have put so many variables, so many height and this and that. After that, they are, discussing that, oh, this is the problem. So that is what happened with this guy also. He just said that we have got this result. And I think in that case, Dr. Rajiv is also involved in all those discussions when the students comes. So this is with fire one. So he got the coefficient 0. Then I said, okay, can you show me your data distribution? He never thought, but when we see the data, this is the way. This is what I showed in the previous, in my initial slide. Because this is very good example. Many times I am giving this example in my talks. Okay, first thing is, yeah, this is not required and this after 40 it is not, fine, discard it. Then I took from 0 to, suppose we can take 0 to 40 only, fine. But still, skewed. That's what you told, no? Still it is skewed. So, started working on the transformation. See, if I tell, okay, go with this particular transformation, then the student will forget after 1 month. Then he says, you told, that's why I did. This is the common answer from BTech to the even PhD student. He told, so I did it. So better, student has to find out what kind of the transformation he did. So then he started doing the transformation every day or every 2 days. He was coming, I have got this. I don't know, this is not working. Okay, I have got this. No, this is not working. This will not go, don't go for the model training. Finally, so many things he has done. Then he said, okay, I'm going to normalization. Okay, do the normalization. After the normalization also, we don't have the proper shape. So the thing is like he did per day normalization, min max normalization, many things, but still the data is not proper. Okay. Finally, what he did after the normalization, then he found, okay, he did log a plus x, no, log ax then continuously changing value a is equal to 1, 2, and so many things, not proper. And he took, I think, few weeks to come back. And then he said, this is the final transformation I'm using. And then this is the distribution. So this is what, and then he put the model for the this Delhi, Punjab, Haryana region. I have 2 to 3, okay. So I should go faster. So now initially he wrote how many layers? 5 layers. 5 more, okay. Then I will go fast. I made the story so that I hope that they understood the importance of the data pre-processing. Okay, so this is what the model he developed later on. But one more story is here. We developed a model for Delhi, Punjab, Haryana. We got very good result and all. But it was not enough. We had the data, and his thesis was like you had to do for different geographical area in Indian subcontinent. So we have these 3 areas. What he did, he took this model, developed the model. He spent so much time, 2-3 months, and developed the model. He said, oh, apply here, apply here. No, it did not work. One difference is that Here it is September to November because we were worried about the pollution in the NCR due to the stubble burning in the Punjab and Haryana. Here it is the forest summer fire. This is due to only the forest fire. That was the only difference. The time zone, time duration is different. But he used the same model, it did not work. Then again he has to find out what to do. It was a master project. He has to find out. It's a research project. So one thing is, then he again started working on the other variables. Okay, what are the variables? You see that this is spatial resolution and time resolution. For Delhi, Punjab, Haryana, it was stubble burning. Even one or two variables were okay because it is not a natural thing. It was man-made stubble burning. But once you go to the other area, it is a forest fire. All the natural things are responsible. All these variables are responsible. Okay. So first thing is we have to change the spatial resolution, temporal resolution, everything we have to make it in the same, whatever we have PM 2.5, 0.1 degree. So we have to do everything in 0.1 degree. Everything we have to make it daily. Then we can. So you see that in the PM 2.5, we have the log x plus 1, but all other, it was not needed. The distribution was okay. So that's why I'm highlighting it. Everything you will find in the paper also. One thing is how we are doing the imputation. Okay, this NDVI is one variable which was required in the northeast area, not in the Delhi, Punjab, Haryana area, not the central India. It was required in only in the northeast because it was for big dense forest. So this vegetable index was index was required and it was giving better results. Okay, imputation. I will not go much, but we have done how we are filling this area that we did. What I wanted to tell you here, see the difference. We don't have much time. This was the Punjab Haryana model. We have to do lot of work to find out why the model is not working. Although almost a few variables we put it, but the model architecture is changed. What to change? Not only that the kernel size, but we have to do a lot of experiment. You see here all the ReLU. Here it is mostly 10 hyperbolic and the one ReLU. Another one is that here we have extra putting the NDVI variable and then the layer went to the 7 and see mostly the last output layer is the ReLU, all are the 10 hyperbolic. So this is the hyperparameter tuning. Data is same, source is same, location is changing, and people are generally not thinking about the same location, satellite data, okay, work here, and same model will work. No, it doesn't. And still there is debate. I have many, discussion with the people. People in the Europe, they are saying, I have developed the model for Italy, it will work for your India. I said, okay, let it see, I will give you the data. It's not necessary you are working and developing model somewhere else and it will work everywhere. It's not necessary. Okay, so I will not go to these results because time is. So I'm saying that after doing all those things, then the results came very nice. All this RMSE, spatial correlation, everything in all the three areas were very good. So now this is the take-home message, which already I have told you that you have to give the attention on the data, which data you are working. Whatever you learned till now in the workshop, it was what kind of model, what is the mathematics and all, but this is additional things you have to note down. Okay. So I will not read it, but if you have the question, I can go for the question now. Yes.
On there was monthly data and you converted it to daily.
No, monthly is not daily, no.
Okay, so if you go previous.
Monthly, daily, I don't think so. We have done.
Previous, sorry, hourly.
Hourly to daily we can do.
And then 0.25 cross 0.25 to 0.1.
Yes, because we have to make, because this guy is the main target. This is 0.01. 0.1. So we have to make everything 0.01.
So it's super resolution kind of thing.
Yeah, we can do pooling and all. Huh? Yes.
Yeah.
Okay. One by one.
Thank you, sir. I have a couple of questions. First, like why like NDVI used only for Northeast? Because I think you need like few.
I put the NDVI in the other area also. No improvement. See, in the Delhi, it is the man-made things. They are burning the crop and the smoke is coming, and that's why PM 2.5 is coming, and that's what is captured by the satellite. But in the forest fire, central India is dry. It is very much heat. Then the fire is coming. Okay, and the trees are very less. But in the northeast, I have covered not only India, it's even Thailand and all it was covered. There was dense forest. Then this index, this variable was giving better performance. It is giving some contribution in that.
But you need fuel to burn, right? So for fire, you need greenness everywhere. Even
If the
for
more
croplands.
forest is there and the more temperature, then it will give the more fire, no?
And why this NDVI is used from NOAA? That is very coarse. There is modified.
That is different. That is another question. How I got that? What is the data source? The project came from the air pollution department. They gave me the data. I worked as a AI guy there. In the as a HPC scientist, I work with them. So whatever the data they were giving, I used. Yes.
And sir, there are like already like ready to use products that need not be pre-processed a lot using prior to using in AI models. What is your take on that? The development of data.
This is the shortcut. If you are saying everything ready to use, here we are discussing. Suppose
Not everything.
you want to make a product. No, you want to give a product to someone else. How will you make?
I will make it ready to use. There is no chance for somebody else to pre-process it to make it process. Data these days, a lot of data are ready to use.
Data is ready to use, then is fine. But I said that suppose you are the person who are making the data ready. Then initially I said, suppose you have the access to the live data from radar or somewhere else. Then how to do? So you are talking about at the end user. I am getting ready data. I am getting ready model. I am not going to reprocess it. That is a different issue as a end user. But you are sitting here in a workshop in the ICTS. We are discussing in the mathematics and model development and how to improve the model. In that sense, I am saying, suppose you are the guy who is preparing the data. Then what to do? Then you have to take care of all those things. No. So think in that way. Not the end user, maybe the first person.
Thank you.
Okay, yes, you have a question?
I was thinking we can discuss this later. Like if
Okay,
anyone else has
fine. Yeah, he has more question.
So, sir, during data pre-processing or preparation, you said that if the data is skewed, we all go for some kind of Gaussian or symmetric kind of distribution.
Yes.
Correct. Now, for example, if I'm training rainfall data, specifically for India, with different homogeneous regions, and I'm trying to train data, we know that it has a very different type of distribution, gamma distribution, but not. Is it always possible that when I'm doing this variable change or some kind of transformation, I'll get a symmetric distribution? Always possible? Is it always possible?
Always possible, Boyan. What kind of mathematical transformation you are using to make it the Gaussian? If you see the radius on the data, I told no. Even here in this data, how many transformation we have used?
You are doing a layer of transformations.
No, not the layer. You have to find out which is working in this, but only one transformation you have to use it.
Correct.
So in this case, like Vox-Cox was used, where here we did not do any transformation, but yeah, look at different data, different transformation. It doesn't mean we are using one by one. Only one we will use. Which one is getting me this kind of distribution? That is the main game. I mean, main aim.
And it has to be always a symmetric kind of distribution. Like
I told you why.
Correct.
I told you already, Ratish sir told that why when we do this optimization thing and we are going to gradient descent and gradient, we have to find the solution. And it goes step by step. It should not diverge. It should converge. It will converge when we have this kind of shape.
Another thing is like, how do we identify outliners in the data during the
outliers that you have to do manually, or if you have some ready-made like something software, you can find out. And also, I said that in case of the the radar data, how do you know it is outlier or not? Then you need the domain knowledge as well. As I said, for the 15 minutes, can you get the 1000 millimeter rain? No. So there is an outlier. You have to remove it. Also, in the radar data, suppose you don't know whether it is filter or not. If you get the size, suppose you are seeing the reflectivity and so big reflectivity and size is like centimeter, it cannot be rainfall. Those domain knowledge is also required. Wait, we have time. Okay.
Sir, I have a question regarding the data pre-processing.
Yes.
So we are pre-processing the data to bring it, to bring the
Proper shape.
distribution to a proper shape, and the convergence will be faster, or that's the reason we say. Let's say I have a model which predicts cyclones based on sea surface temperature, or some other parameters.
You have already made the model without worrying about the
No.
shape. Huh?
No, I'm just hypothetically asking. So we have a model. I want to make a model which predicts cyclones based on some other parameters such as sea surface temperature. So it will predict the sea surface pressure, SLP. So it's in hectopascal, right? So we are giving the model sea surface temperature, which is in Celsius or Kelvin, and then we want to predict hectopascals. Okay, so we usually normalize the data, right? Because they are in different
Yeah,
units.
you have to normalize it. Everything will be denormalized. Don't
Yeah,
forget
so
this.
that's where my question is. So we are, let's say, giving the historical data, and the sea surface temperature minimum or the maximum sea surface temperature is 30 degrees Celsius. So
Yes,
the
yes.
data, if in the future, when we are going to predict, we are going to give a sea surface temperature which the training data set does not have. Like we are going to give some unseen SST, like 35 degrees Celsius or something. So that will go out of the normalization, right? It will, if we apply the same denormalization, which is
I think you are mixing. Normalization, everything is being done during the training time for the training data only.
Yes.
Unseen data is as it is.
yes,
When we are going to apply the model on the unseen data, everything coming back to the original space, original denormalization, everything same. So suppose you have the MLD is going from 0 to 100 meter. Okay, you have the SST is in the, suppose Bay of Bengal, it is varying from 25 to 32 degree. Everything, all thing we first brought into 0 to 1. Then finally, when the model is done, we are again bringing back. Or if you are want to do the testing, even in the same testing data also, you want to do the 0 to 1, do this. Do the testing. But when you see the result, everything you have to denormalize. Every variable has to be denormalization based on its range and unit.
so the denormalization will be based on the
Based
range
on
of
how
the
did you do
output,
the normalization. Yes. For
based
each
on the
variable.
output. The denormalization will be based on the range of output, not the input. Like the input data will have a
It is
range.
different. It is same. See.
Yeah, so that's
You-
where my question is.
You have the SST. I'm saying it is 22 to 31 in the Bay of Bengal. This interval you went to 0 to 1. Okay. Then you had the MLD or some other turbulence variable. This guy is generally how much it varies in Bay of Bengal. Maybe it goes, suppose 0 to 60 meter. This is in the meter. This again, you put it into the 0 to 1. How? Based on this interval and based on this interval. And once it is done, everything you have to bring back in the same thing using whatever the formula you have used for the normalization based on these alpha and beta, these alpha 1 and beta 1. Same formula you will use to inverse transformation to bring back to the your original things.
Yes, I got it, sir. So now the question arises is that when we denormalize it, the output will have the same range as the input, right?
Yes.
So we will not
Otherwise,
be able
how
to
to
predict
understand?
extremes.
Yes.
So we will not be, my question is, we will not be able to predict extremes, right? Which is out of the range of the input data. Like I will not be able to.
You are talking about the outlier or you're talking about extremes?
Output. I mean, my model is going to predict whatever, let's say MLD. So the prediction will be, restricted to the input range only, right? Like it will
Not
only predict
necessary.
from 0 to 60, right? It will not.
No, not necessarily.
60.
This range is basically used for the calculating the weightage. It's not necessary that I have fixed it here, it will come into, no, it's not necessary.
Okay.
Yeah.
If it's a part of the distribution of the Gaussian distribution, it should come as a part of the model frame.
Yeah, I mean, so
No,
if
I
it
don't know it is
something-
extreme value or he's saying that if it is not into, okay, it is not, is outlier, then it can be extreme also. Yes. Either the minimum size or maximum size.
Oh, okay.
Extreme is still difficult. We are debating for what kind of model. That's why the attention model have come, transformer and all has come. Yes, sir. Have you,
Let's thank Bipin for this talk on a very practical aspect.